It's a simple question. Why can't you go faster than light? It feels like you should be able to. If you're in a car going 50 miles per hour and you throw a baseball forward at 50 miles per hour, the baseball is now going 100 miles per hour relative to the ground. That makes sense. Our brains get that. It's just addition. So why can't you do that with light? If you're on a spaceship traveling at half the speed of light and you turn on a flashlight, why doesn't the light from that flashlight shoot out at 1.5 times the speed of light? The answer is strange, and it's not just because it's a rule somebody made up. It's not a cosmic traffic law. It's woven into the very fabric of reality. The speed of light isn't just a speed limit for things moving through space. It is the speed of space and time itself. To understand this, we have to throw out some of our most basic ideas about how the world works. We have to learn to think like Einstein. For a long time, everyone thought like Isaac Newton. His laws of motion worked perfectly. They described how apples fall from trees, how planets orbit the sun, and how cannonballs fly through the air. And a key part of Newton's world was that space and time were absolute. A meter was always a meter, no matter who was measuring it. And a second was always a second. They were the fixed, unchanging background of the universe. The stage on which everything happened. In this world, speeds just add up, the car and the baseball. Simple. Then, in the 1800s, a scientist named James Clerk Maxwell came along. He wasn't trying to break physics. He was studying electricity and magnetism. He came up with a set of beautiful equations that described how these two forces were really just two sides of the same coin, electromagnetism. But hidden inside his mouth was something bizarre. His equations predicted that an electromagnetic wave, like light, would always travel at a specific speed. This speed was about 300,000 kilometers per second, or 186,000 miles per second. We call this speed sick. Here's the weird part. The equations didn't say what the speed was relative to. They just said the speed of light is kid. Always. It didn't matter if the source of the light was standing still or moving on a super fast train. The light it emitted would always travel x. This flew in the face of everything Newton and common sense told us. It created a huge conflict in physics. Either Newton's simple addition of speeds was wrong, or Maxwell's brilliant equations about electromagnetism were wrong. For decades, physicists were stuck. Then came Albert Einstein. In 1905, while working as a patent clerk, he published a paper on what he called special relativity. He started with a very bold idea. What if Maxwell was right? What if the speed of light is constant for everyone, no matter how fast they are moving? Let's just accept that as a fact of the universe and see what happens. This one simple idea, that the speed of light is constant, has staggering consequences. If the speed of a thing is distance divided by time miles per hour and you decide that the speed part of that equation can never ever change for light, then the other two things, distance and time, have to change instead. They are no longer absolute. They become relative. They become flexible. Let's imagine a light clock. It's a simple device that has two mirrors facing each other. A single particle of light, a photon, bounces back and forth between them. Every time the photon hits a mirror, the clock ticks. If the clock is just sitting on a table in front of you, the photon travels a straight path up and down. Tick, tock, simple. The distance is short. Now, let's put that same clock on a spaceship flying past you at a very high speed. From your perspective, standing on the ground, you see the clock whiz by. The photon is still bouncing between the two mirrors. But because the clock itself is moving sideways, the photon is no longer traveling a short straight path up and down. To get from the bottom mirror to the top mirror, it has to travel on a diagonal. That diagonal path is longer than the straight up and down path. This is the crucial moment. We've already agreed on Einstein's one rule: the speed of light is constant for everyone. So the photon in the moving clock is traveling at the exact same speed as the photon in the clock sitting on your table. But it's traveling a longer distance. If it's going the same speed but has to cover more ground, what does that mean? It must take more time. From your perspective, the moving clock is ticking slower than your clock. Time itself is running more slowly for that spaceship. This isn't a trick. It's not that the clock is broken. The flow of time itself has slowed down. This is called time dilation. The faster you move through space, the slower you move through time. This isn't just a thought experiment, it's real. We see it all the time. GPS satellites orbit the Earth at high speeds. The clocks on those satellites run slightly slower than clocks on the ground. If engineers didn't account for this time dilation, your GPS would be off by several miles every single day. We've also tested it with incredibly precise atomic clocks on jet airplanes. They come back to the ground having measured slightly less time than the clocks that stayed behind. So, time is flexible. And because space and time are linked together in what we call space-time, space must be flexible too. If you were to measure that fast-moving spaceship, you would find that it is shorter in the direction it's moving than it would be if it were at rest. This is called length contraction. The universe literally shrinks space and slows time to make sure that no one ever measures the speed of light to be anything other than c. Space-time itself contorts to protect this universal speed limit. This brings us to the first big reason why you can't break the speed of light. The closer you get to it, the more space-time works against you. From an outside perspective, your time slows down dramatically and your length shrinks. You are experiencing the universe in a completely different way, but you can never quite get to that finish line. But there's another, maybe more intuitive reason. It has to do with energy and mass. We all have a basic idea of what mass is. It's how much stuff is in an object. It's also a measure of inertia. Inertia is an object's resistance to being pushed. It's easier to push a bicycle than a freight train because the train has more mass, more inertia. To make something go faster, you have to push it. You have to give it energy. In Newton's world, this was straightforward. You keep applying a constant force to an object, it will keep accelerating, going faster and faster forever. There's no limit. But Einstein showed this was wrong. He came up with the most famous equation in all of science, E mmc2. Most people think this equation is just about bombs, but its meaning is far deeper. It says that energy and mass are two sides of the same coin. They are convertible. You can turn mass into a huge amount of energy, but you can also turn energy into mass. Now, think back to pushing our spaceship. We are firing up the engines, applying force, and pumping energy into it to make it go faster. At first, when the ship is moving slowly, almost all that energy goes into increasing its speed, just like we'd expect. But as the spaceship gets closer and closer to the speed of light, something strange starts to happen. More and more of the energy we pump in stops increasing its speed and starts increasing its mass instead. From an outsider's perspective, the spaceship is getting heavier. Its inertia is increasing. It gets harder and harder to push. It's like you're trying to push a car, and as it gets faster, it slowly starts turning into a truck, then a train, then a mountain. You're still pushing with the same force, but you're getting less and less acceleration in return. All that energy is being converted directly into mass, according to EMC2. So, what would it take to actually reach the speed of light? As you get to 99% of the speed of light, your mass is already increased by a lot. At 99.9%, it's much, much bigger. At 99.99999%, you are enormously massive. To get that last tiny little bit of speed to reach 100%, you would need to add an infinite amount of energy, because your mass would become infinite. And there's the roadblock. The universe doesn't have an infinite amount of energy to give. You can't have an object with infinite mass. So no object with mass, whether it's a spaceship, a baseball, or a single electron, can ever be accelerated to the speed of light. It's physically impossible. The universe simply runs out of energy to get you there. The energy cost becomes infinite. This raises an obvious question. What about light itself? How can light travel at the speed of light if nothing can reach it? The trick is that light never had to reach that speed. Particles of light, photons, are born at the speed of light. They have zero rest mass. Because they are massless, the rule about infinite energy doesn't apply to them in the same way. They don't accelerate from 0 to cool, they're natural, and only state of being is to travel at. They can't go any slower or any faster in a vacuum. It is their one and only speed. For a photon, time doesn't pass at all. From its perspective, its journey from a distant star to your eye is instantaneous. The start and end points of its journey happen at the same moment. It experiences no time and no distance. So we have two very physical reasons why the speed limit exists. First, space-time itself warps to keep the speed of light constant. Second, the energy required to accelerate an object with mass to that speed is infinite. But there is a third, even deeper reason. It has to do with the logical structure of the universe. It's about cause and effect. We live in a universe governed by causality. Cause comes before effect. You flip a switch, then the light turns on. You drop a glass, then it shatters on the floor. The effect never happens before the cause. This simple logical sequence of events is the foundation of our reality. Without it, the universe would be a nonsensical chaos of paradoxes. The speed of light is the protector of causality. It is the maximum speed at which information or any causal influence can travel through the universe. Let's see what would happen if you could break this limit. Imagine you have a spaceship that can travel faster than light. You and a friend on Earth decide to do an experiment. There's a space station orbiting a star 10 light years away. Your friend on Earth sends a message to the station using a regular radio signal, which travels at the speed of light. It will take 10 years for that message to arrive. You get in your faster than light ship and race the message. Because you can go faster than light, you get there in, say, 1 year. When you arrive, you send a message back to Earth using your faster than light communicator. This message says, I beat your radio signal. It hasn't arrived yet. From your perspective, everything seems normal. But remember, time dilation. Time passes differently for different observers. For someone on a third ship flying by at a different speed, the order of events could look completely different. Because of the weirdness of relativity, for that third observer, your faster than light signal going back to Earth could be seen as arriving before your friend on Earth ever sent the original message. Think about what that means. Your friend on Earth could receive your reply to their message before they have even decided to send it. They could get a message that says, I got your message, and then decide, well, now that I have the reply, I guess I won't bother sending the original message after all. The whole thing falls apart. The effect receiving the reply has happened before the cause, sending the message. This is a grandfather paradox. It's like going back in time and killing your own grandfather before he met your grandmother. If you did that, you would never have been born. But if you were never born, you couldn't have gone back in time to do it. It's a complete breakdown of logic. A universe that allows for faster than light travel is a universe that allows for time travel into the past. It's a universe where causality is broken. The speed of light isn't just a speed limit, it's a causality barrier. It ensures that the universe plays out in a logical, orderly fashion, where the past influences the present, and the present influences the future. Not the other way around. This might be the most profound reason of all. The speed limit exists to keep reality from dissolving into an incoherent mess of paradoxes. Now, you might have heard of some ideas that seem to challenge this. What about warp drives or wormholes from science fiction? These are clever theoretical loopholes. A warp drive doesn't propel a ship through space faster than light. Instead, it would work by warping space-time itself. It would compress the space in front of the ship and expand the space behind it. The ship would be riding in a bubble of normal flat space-time, and this bubble would be moved, carrying the ship with it. The ship itself never locally breaks the speed of light. It's more like you're standing still on a moving sidewalk. You aren't running, but the sidewalk is carrying you forward quickly. It's a way of taking a shortcut by bending the rules of the road, not breaking the speed limit of your car. These ideas are purely theoretical right now and would require forms of matter and energy that we don't know exist. Another common point of confusion is the expansion of the universe. We observe that very distant galaxies are moving away from us faster than the speed of light. This seems like a clear violation of the rule, but it's not. The galaxies are not flying through space at that speed. The space between us and those galaxies is expanding. It's like drawing two dots on a balloon and then blowing it up. The dots get farther apart, but they aren't crawling across the balloon's surface. The fabric of the balloon itself is stretching. The expansion of space itself is not bound by the speed of light. The rule is that nothing can move through a local patch of space faster than, say. The galaxies are obeying that rule perfectly within their own local area, so where does this leave us? The speed of light is much more than just a number. It's a fundamental constant of nature that shapes the very essence of reality. It tells us about the deep connection between space and time, between mass and energy. It's the ultimate speed limit for three intertwined reasons. First, because it is constant for all observers. It forces space and time to become flexible, to stretch and shrink in just the right way to uphold that constancy. Time slows down and space contracts as you approach it, making it an ever-receding goal. Second, because of the equivalence of mass and energy, an object's inertia increases as it speeds up. To reach the speed of light, an object with mass would need an infinite amount of energy, making its mass infinite. This is a physical impossibility. And third, it serves as the universe's causality enforcement agent. By limiting the speed of information, it ensures that effects always follow their causes, preserving the logical structure of reality and preventing the universe from collapsing into paradox. It's a strange and beautiful idea. Our everyday intuition, built on a world of slow-moving objects, simply fails us when we start dealing with the cosmos at its most extreme. The universe doesn't care about our common sense. It operates on a much deeper and weirder set of rules. The speed of light isn't an annoying restriction, it's a cornerstone of the entire structure. It's the rate at which reality itself unfolds. It's the reason the universe makes sense.